let's call it 2. Then in my working I say substituting 1 and 2 into star gives me the answer. Right, look at that, jot it down if you need to, because I need to start a fresh piece of paper. So I say substituting 1 and 2 into star, I get so 1 over f this bit is f prime that x minus 1 is going to cancel one of those x minus 1's. That is a quadratic. Leave it as it is because I can't easily can't factorize that thing. And done. And this is for all x. Let's have a look. Well, for what x can this take? For all x on the real line except for x equal to 1, because look, for this function, if you put x is equal to 1, you're going to be dividing by 0. And we can't have it less than 1, because if it's less than 1, then this is going to be a negative number, and we just said you can't take log of negative numbers. The top bit is always going to be positive, so it's going to always, if x is less than 1, then you're going to get a positive number divided by a negative number, so that can't be true case. So it's for all x bigger than 1 is where this derivative exists. Bigger than 1. Bigger than, yep. Okay, so that is the answer. Now I want to show you another way of doing this. Could be quicker. We're using the log rules. Notice, recall that a and b are positive numbers. Log of a times b is same as saying equivalent to log of a minus log of b. Alright? So if we apply it here, we can see that my h function is going to be log of x squared plus 1 minus log of x minus 1 for x bigger than 1, positive values. Alright, otherwise this function here, you can't calculate it otherwise. And now what we can do is, we want the derivative of h, look, we can use the sum rule, do it on each term, find derivative of each term, and we can apply the rule for logarithms, chain rule for each term. So for this one, it's going to be 1 over this, and up here will be the derivative of what's in the bracket here, which is 2x. Same with this one, minus x minus 1, derivative of this thing, there. So by using the logarithm times a product, we can break it down into simpler components, in which it's easier to find the derivative. Alright? Now this should be the same as what we've just done. We could leave it like this, or we could try to get it to look like what we've just done. So using basic math, I know basic math isn't something that we could be rusty on, so how did I get this? Take a common denominator, alright, that times that, but if you do that times that, what you want to do is take this up there, like that, and then subtract, in this case, that times that, which is what I've done here. Okay, and that works, because look, if we look at this, this is going to be equal to that. Why? Two terms here, this bit here, so let's look at this bit. Well, if you look at this bit here, you can see the x minus 1's cancel, which leaves us with this term. And for the second term, look, it's this second term. If we just look at this second term, we see that x minus 1 cancel, leaving us with that. So that's why it kind of works when you combine these two as a product on the denominator, like so, and then take this up there and this over there. That's why it works. Right, expand brackets and should be Bob's your uncle. Let's just say the numerator. It saves us having to copy this each time. Okay, so that's the numerator, x squared minus 2x minus 1. Aha, x squared minus 2x minus 1. And then bottom bit should be the same, from which look I see that, oh, I was very careless here. Take your time when you're doing proofs, I mean these kind of questions. There you go, I missed that, didn't I? That was my answer up there. Well done, you spotted that. And then you can see now it matches the denominator for this one. So we're done. Okay, so that is differentiating with log and exponential. And finally, as a parting note, some of you might ask me, well, for this final example, this top bit looks like a quadratic. It is a quadratic, so is there any point completing the square? Well, if you're completing the square, you'll find that it's quite useful, because you'll be able to tell whether or not the derivative can be 0 at any point of x. In other words, you can see if there's a turning point anywhere. In other words, by completing the square, you can see whether or not this thing is 0 for any value of x. Or you could use the quadratic method. Okay, so that ends this video.